Hi there. Thank you for showing up for your learning periodically, as you're known to do. And today is a very terrific Thursday that I'm unable to attend, but I am able to come to you digitally to share with you the new knowledge. On your desks, you want to have your handout package from yesterday. You want to have a pencil, perhaps some other colors that you can use to give some life to your graphs. And you also want your thinking caps on. Anyhow, let's get started. I want you to start thinking about this example of a bike tire. Let's say that there was a very cute ladybug on the on the inside of the bike tire, and we wanted to model the ladybug's position vertically. How high is the ladybug as you ride your bike? And I want you to start thinking about what that graph would look like and how you could create a function that could model its position perfectly. So let's keep thinking as we go through these lessons about that ladybug on the inside of the bike tire. Maybe name the ladybug so that you care about where this ladybug might be found. All right, so we're introducing sinusoidal functions, periodic functions, trigonometric functions. You'll hear all different ways of talking about this, but you won't hear cosinusoidal functions. That would be weird. I just invented that word. All right, so you should be able to, by the end of today's lesson, sketch the graph for the parent functions sine and cosine. And you can use the unit circle to do so. Hooray! You can also use your calculator. Unit circle for style points. You also want to know like what the amplitude, the period, and the equation of the axis is for these parent functions. We also want to think about the domain and range, particularly the range of these functions. This is particularly useful. Now, sinusoidal functions, they're these like transform trigonometric functions that we're going to look at soon. You can think of them as waves. And here you see a sinusoidal function waving around that horizontal axis. So the amplitude, that's why we don't measure the amplitude is from the top to the bottom, but from the top to the middle. That's like the height of the wave above sea level. And what about this unit circle is going to be so useful to us when we're graphing these things? Well, we have some ideas here about how we can think of like if this angle theta here, which we have here, clicking to show you my cursor advances the screen. So this theta here, as theta grows, you know that y is going to grow, and that's going to be related to the sine of that angle, and the x is going to shrink, and that's related to the cosine of that angle, until the x starts growing again and the y starts shrinking again, and so on and so forth. And they're gonna continue this relationship. So what we're going to do? We're going to do this together, actually, not with a partner. So this is a beautiful visualization of how see the vertical dimension of the unit circle as it goes around in the circle. The vertical dimension is being recorded as sine of theta. And then the horizontal dimension, we're just rotating that 90 degrees and then graphing it along the same axes there to represent cosine of theta. So I'm just going to let you sort of drink in the beauty of uh, this representation while I take a sip here. I need students in the room to keep the lights on. All right, we'll save some power here. So now let's go ahead and graph f of x is equal to sine x. And I'm going to go through this with you on the handouts that you have. So get your handouts out. You've got your sine value function. First thing you're going to start with is a table of values. And this is a very popular question to ask me. Where do these x values come from? Let me tell you how I chose the x values. We're going to be graphing one full cycle of the sine function. We want enough detail. The points we absolutely want to hit are related to where sine is at its maximum. Okay, so let's see. All right, so at its minimum, oh, that was 270. It was at its maximum, it's at 90. Oh, sine is at its minimum, it's 270. And also the places where it crosses the midline are really important points to have on your graph. So those would be 0 degrees right there. And here it comes, 180 degrees. Okay, so those are definitely things that we want to have on our table of values. And so you'll notice that they're there. But we want more detail than that. We don't want just like a sawtooth line going between the maximums and minimums, because it's not shaped like a sawtooth. It's really a beautiful curve. So anyway, here is like where sine is at its maximum. The value of sine x is 1 there. When x is 0, the value of sine x is 0. We saw that when x was 180, the value of sine was, again, 0. And at 270, the value of sine is at its minimum, -1. At 360, well, we're back to 0 degrees. 360 is the same as 0. It's back to 0. Okay, so those are some really key points to have on our table. But then, let's also put the special angles on there to give us some more detail. And I chose to put them in 2 quadrants only. Why did I do that? I figured you're going to see what's happening there, and then you can visually put them on the other side. So let's see. The value of sine 30, the exact value is 1 over 2. If you prefer a decimal, it's 0.5. The exact value of sine 45, we get it from our unit circle. Okay, I'm going to get it from my memory because I remember these things. All right, and this is 1 over root 2. And that is, I think it's 707. Let's see, clear. And then, of course, you can just do this. You can just say, well, 45 degrees, but I take the sine of it, and that's 0.707. Okay? And 0.7 is enough detail. I can't show more detail than that on these graphs. So that's 0.7. You don't need a giant long decimal. Remember, you're creating a graph. And then next, 60 degrees. Oh, well, that's root 3 over 2. Cool. And let's just see what, if I have 60 here. Okay, 60. And I take the sine of it. That's 0.866. Okay, so 0.87 is a lot of detail. For graphing purposes, if you're doing a word problem or something, you want more decimal places than what I'm doing here. I can only show so many decimal places in the graph. 0.87. Like very nearly 0.9. All right. And then what about 120? Oh, well, I remember that that's root 3 over 2. Or I'm not going to write down the decimals anymore. Can't make me. All right. 135, that's 1 over root 2. And then 150, again, we're back to 1/2. Okay. Now, we've got this table of values filled in. You'll notice I didn't put the special angles for the other quadrants, but you're going to kind of reflect in the x-axis and move over. All right. Now, we're going to go ahead and use the whole graph. This is 1 up here. This is -1. Okay? Why? Because we want to show a nice, big, beautiful curve. You don't want to like use this as 1 and waste 3/4 of your graph. All right? So when the angle is 0, the value of sine is 0. Here is 30 degrees here. Cool. At 30 degrees, it's a value 1/2. So we're already up there. Okay, because that's 0.5. This could be 0.75, and this would be 0.25. We don't really have any points in there. Okay, so this is 60, and at 60, we're already up here at 0.87. So if this is 7.5, that'd be about 8, that'd be about 9. We're already like about there. I would say we're about like that. And then at 90, we're at 1. All right, and let's get 45 in there. 45 is going to be right in between 30 and 60. So this would be 45 degrees. You can write it on because it's not on there on your scale. And then you can come up, and it's a little bit less than 0.75. It's like there. Okay, cool. I'm beginning to see the makings of a beautiful curve. And now 90, we're going to go out to 120. Here's 120 right here. And we are parallel with this one. Boop. And then we're going to go over to 135. We're going to grab this one. Boop. And 30 degrees, we're going to grab that one. Boop. All right. And then we're down here at 180. So that's 150 over there. Sorry, I said 30, but it's the same as sine 30. All right, now let's do the positive part of sine. And we're going to graph a beautiful curve here. Cool. Okay, there we go. So that's the beginning. And now let's go ahead and put the rest of our table of values on. 270 is at -1. Okay, boop, down here. One trick that you can use when graphing transformed ones is you can put a little dotted line for the horizontal axis. I'm not going to do that here because it's the x-axis, but you can also, if you recognize the maximum and minimum values, you can put a little dotted line along there. And it's not to say that it's like an asymptote, but it's just a guideline for you that your function is going to oscillate between these two values. Okay, so we can do that. And then I'm going to go ahead and go back to blue. I've got that point on, but then I'm going to say, well, I recognize here that I'm at 1/2. If I was at 210, I would be at -1/2. And then just check that on your calculator to make sure. You're going to go, wait, clear. I keep on forgetting. 210, but I take the sign of, -1/2. Okay, cool. What I'm seeing visually is being confirmed calculatorally. All right. And then what else would be 1/2? Well, 330. Okay. And then what about the barbell numbers? My 225? Well, that would be the 0.70. So that's like there. And the 315, that would be 0.70, but they're both negative. And then how about these numbers, 240? 240, well, that would be this one here, this point, but reflected in the x-axis and moved over here. So that's like almost 0.9, 0.87. So we're like there, and we're like there. Okay. Now we've got our beautiful sine curve. Yeah. Oh yeah, hitting points. All right. And then you can put an arrow on that to indicate that it's going to go through another period and continue this pattern forever. All right. And now let's take a look at the properties of the sine function. So what's his maximum value? Well, I read that off the graph. It's 1. That's important. What's his minimum value? I read it off the graph. You can answer these without my help. -1. What's its y-intercept? Oh, it hit the y-axis at 0. Where are the x-intercepts? 0, comma, 180, comma, 360, dot, dot, dot. That's going to create an arithmetic progression, okay, an arithmetic series. You just keep adding 180, and that's going to be where it bink, bink, bink keeps hitting the x-axis. What's the amplitude? Okay, well, let's see. Let's change colors. All right, let's show the amplitude here. The amplitude is 1. Okay, the amplitude is 1. Why? Well, the minimum is 1 below the horizontal axis. The maximum is 1 above the horizontal axis. You ain't going to get me to do that algebraically. I know it's 1. Okay, the equation of the axis, well, it's the x-axis, and that happens to be y equals 0. Now, what's the period? Okay, remember, the period is the length of time it takes for, not the length of time, but the amount of x values that it takes for this function to go through one cycle. And that's 360 degrees. That's one time around the circle. Okay, 360 degrees. What's the domain? X can be any number. X is of the reals. Now, what's the range? What's the range of this function, everyone? Well, y is also real numbers. We got weird decimals and fractions and things, so it's certainly not integers. But y's are the reals, and -1 is less than or equal to y, which is less than or equal to 1. Those are the maximum and minimum values. It never goes bigger than that, never goes smaller than that. That's why your calculator says error when you try and stuff something in like, give me the inverse sine of 7. It will say, I can't do that. It's outside the range. All right, so let's take a look at cosine, and we're going to go a little faster now. All right, actually, I'm going to let you do cosine on your own. Because you should be able to after seeing sine done. So if you have trouble with that, definitely ask your table mates for some help getting the cosine graph done. Set up the scale of your y-axis in the same way and get a nice beautiful curve. And I wish you all well. If your handout doesn't look like this but is missing all that, it's because the y-intercept, the y-intercept, I should have had the y-intercept on there. But the maximum and minimum value for cosine are the same. It's just y-intercept is a little different. So anyway, that is that, and that's it for me. After this, you can go ahead to, once you've got your sinusoidal functions graphed, your parent functions, go ahead and try some marble slides in Desmos and get your hands on some Chromebooks and play with transformations of these functions. And just to conclude, let's go back here. Boop, 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 boop. And we want to think, we've done sin x, cos x. And just the last thing is think about this bike question. If the bike tire were bigger or smaller, how would that affect the graph? What factors would it change? Like, use your new vocabulary. Horizontal axis. What would the horizontal axis be for this function? Like, where would it be? What would represent the horizontal axis? Uh, the height of this ladybug going up and down. What would the maximum and minimum values mean? And what would the period be? All of these questions are good questions to help build your understanding for tomorrow's lesson. So you can think about that. Maybe talk to me about it in the morning on Friday. I'm surely going to be here on Friday. So tell me about your thinking about this question. It's a really cool way to build your thoughts. Otherwise, any questions, hit me up by email. I'll be available all day. And thank you for showing up for your learning.